I think it's great. I think it's definitely like a good idea if you're like looking to get involved in the C++ industry to come, talk to the people, to meet everybody. You never know what can happen.
Welcome, everybody. My name is Daniel Marjamäki. I am the creator of CppCheck. CppCheck. Do you hear? So if I pull down my face a bit. Okay. I'm the creator of CppCheck. CppCheck is a static analysis tool for C and C++ code. We focus a lot on trying to find undefined behavior and real bugs rather than stylistic issues. I live in Sweden. I have a wife, cat, and child. I would say change the order if I could. I have worked professionally with C and C++ for almost 20 years in various industries. So to start with, I worked at a company that made control systems for heavy machines. Then I went to an embedded C contractor. And then I went to writing TV streaming software in C++. And nowadays I work as a CppCheck developer at Fulltime. I will come back to that later a little. And I always want to mention my clothes here. It's my favorite t-shirt today. What will I say today? I will have a chronological walkthrough of how CppCheck was developed from start until now. And I will give you some learnings. Before I started CppCheck, as I said, I worked at a company that produced control systems. I was working in a Borland C++ builder environment, writing C++ code. I made a tool for that control system. At our company, we also had a lot of embedded C code. I was feeling that our quality was not good enough in this, and that we made mistakes. And the compilers would not find a lot of mistakes. I was quite dissatisfied with that. So for instance, the code here you see where a buff is declared, and then there is a clear array index out of bounds. I thought that this should be detected by compilers, but they didn't. And still today, you can't be sure that the compiler will warn about that. So I started looking for off-the-shelf static analysis tools. The major problem I had with that was they didn't support our tool chains. So Borland C++ builder code has various compiler extensions, and that is not handled by any or very few of the tools. And our embedded C code had also very many compiler extensions, C extensions, and no tool handled that. So we could only check a small portion of our code. And at this time, the common consensus was that false positives was inevitable when running static analysis. The idea was that static analysis was about stylistic issues, and that you just have to count on lots of false positives. I didn't want to have that. So before you start a hobby project, there are some preconditions. You need to have time to work, you need to have knowledge, and you need to have perseverance. So I was going on a train every day to and from work. So I sat on the train for 10 hours a week, and I thought I can work on a hobby project in this time. So knowledge, I didn't know anything about compiler theory and nothing about static analysis, but I thought that how hard can it be? Then perseverance, I knew from experience, I had started hobby projects before, that I would give up after about 2 or 3 weeks. So I had to plan according to those preconditions. In a normal commercial project, you decide what you want to do, and very quickly the project size gets very big. So you may have thousands of hours of work in a few minutes planned. In CppCheck, it has been the opposite. I plan maybe 10, 20 hours ahead all the time. 100 hours is a really large package for me that could take months to implement if I only spend an hour or two a day. So my first experiment was that I started experimenting with Perl and regular expressions. And that didn't work very well for my checkers I wanted to implement. So I continued and rewrote it in C++ instead. And in May 2007, I had a CppCheck project locally that I thought was quite good. So I made the first commit. There was only one file in that. So it's a main.cpp. And there was 440 lines of infrastructure code and 665 lines of checkers. And that includes comments and empty lines. So it's not lines of code. The first revision, the infrastructure, was quite simple. So I had made a token list. I tokenized the file, and the only pre-processing I made was when I find the include some file. Then I would include that. But it had no include paths, so it had to be in the same folder. But that worked fine for me to start with. And then the other infrastructure I had was a function to match tokens. And this took two arguments, a token and a string. So in that string, you provided a pattern, and then the match would match that token list according to that. The data in the first revision was quite simple. It's a linked list with tokens. The first revision, the checkers I made, these are the checkers. I will not read all this, but why did I choose these checkers? Because I have seen these mistakes and readability problems in our own code, and I wanted to avoid that we continued to make these mistakes. There is 4 checkers here that still is available in today, but warn about includes that are not needed. That was removed later because it didn't fit in later revisions. So why did I use a token list? I can start to discuss a bit why I didn't join an existing project. Like, for instance, I could have tried to join GCC and wrote checkers there. There was 2 main issues with that. First was I thought GCC code was complex. I didn't know so much about it. And the other reason was that it's not compiler agnostic. I wouldn't be able to use it on our code if I would have gone that path. So some pros and cons of using a token list is that it's pros is that it's a compiler agnostic. It doesn't matter if there are compiler extensions. I can just continue to look and search for the patterns I want to look for. For the code we had at our company, I didn't get many false positives. So you can abuse C and C++ and write very ugly code, and then you could get false positives, but I didn't care so much about that this time. The problem was that I had a lot of false negatives that I couldn't fix easily. So about the commits the first year, we can see here that I wasn't very perseverance strong. In May, I made a lot of work. Then June, July, it faded. Then there was a time when I didn't work at all. I'm not sure why I started to work in February, but I did. And here on the next slide, we can see downloads in the first 3 years. In the first year, I think it's interesting to see that there was a lot of interest in static analysis tools. So even though my tool was very simple, we still got quite some downloads, I would say. Maybe roughly 100 a month or so. But then in July 2008, something happened. And it was not a technical thing that happened here. The thing that happened was that there is a Wikipedia page that lists all the static analysis tools, and CppCheck was listed on that page. And the number of downloads was exploding after that. And it was fun to start working. So here I started to work more and more, and I got more and more contributors after this point. So problem started to happen here. There was reports and bug fixes. So it's very easy to use CppCheck. At this point, you just point it at some folder, and it scans all files. And there was fully well-intended, of course, users that was running CppCheck on various open source projects. They turned on all the warnings they could so that the report was as big as possible, and then they sent that report to some project maintainer and said, oh, look at this, you should fix all these. Fully well-intended, of course, but the project maintainer got a very bad impression of what CppCheck is. But also some users started to pull in bug fixes, and that was very nice. Until 2009, we only tokenized the whole files into a single token list. So, and very simple, no pre-processing. In 2009, I started writing a preprocessor, and it was a very strange and bad preprocessor. So I read the whole files into a string, and then I preprocessed that string. And then after that, I made tokens from. A special feature of that preprocessor was that it extracted configurations. So here in this code example, there are two preprocessor configurations, one where X is defined and one where it is not defined. And there are two bugs in this code. And this preprocessor would list all the defines and generate all the possible configurations that should be checked. And we would preprocess one configuration at a time after that and analyze that. So we would detect all the bugs in the code. And there are a few tools that, I don't know any other tool that does that. So in 2010, we started to implement the symbol database. This contains information about scopes, functions, variables, types. And until this time, the checkers had to have all this information in themselves. But now they could easily look up all this information. In 2011, I started to instantiate templates. And it's a horrible feature to implement, I would say. So as a CppCheck developer, I dislike templates. It's the worst feature they invented. In 2012, we started seeing that the CPU usage was quite high in CppCheck analysis. And we identified that it was this token match function that took most of the time. So we made one attempt with a JIT that would try to compile each pattern into some assembler instructions. That didn't work very well and was not very portable. Then I made another attempt. I wrote a Python script that transformed our original code. So before we compile a release binary, we run this match compiler that transforms the token matching into a function, and then it transforms the if condition, so it calls this alternative function instead. And this was much faster. So I think it's like 80% faster or something like that. In 2012, we also started to implement the syntax tree. You have an expression here, x equals a plus b star c. So if Cppcheck sees this, it will create the syntax tree that is shown. And interestingly, I think that the syntax tree was integrated into the token lists, so that the gray circles you see here, these are actually tokens. And so each token has 2 operands. It's pointers to other tokens, and each token has a AST parent. It's also a pointer. So that doesn't fully fit with the C++ standard, for instance, the ternary operator, but we worked around those edge cases. So each token has 2 operands. Until 2014, each checker had to have its own data flow analysis. So for instance, null pointer dereference, that was one data flow. And if you run array index out of bounds, that was one data flow. But in 2014, we started to implement a generic data flow analysis that was reused by all the checkers. So that was much better. In 2015, finally, I realized that the string-based preprocessing that led to so many problems. Most of the bugs that we had was related to that. And I started to look for alternatives. Can we import some preprocessor ready-made? I didn't find the alternative that I thought would work for us. Either it was hard to integrate into Cppcheck, or maybe it was written in latest C++. In Cppcheck, we want it to be portable, so you can compile it on many platforms, including old platforms, so latest C++ can't be used. With a remark there, we have some tweaks to allow later C++ features. But then I started to implement a preprocessor library called Simple CPP. And this is a separate repository, so it's a separate project, but we use it mainly for Cppcheck. It's open source and BSD licensed, so I want to advertise that a little. Please use it if you need a preprocessor. It's very simple, it's one header and one source file. In 2015, we started to implement something called the value type. So this was added to each token. So if there is an expression like seen here below, then the value type would say that, for instance, the star was a signed int and the plus would be a signed int pointer. Before this 2015, we need to have magic in the checkers to understand this. Here's an interesting bug that we have found that got a lot of attention. There was many articles written about this, and it really raised the interest for Cppcheck. There was a bug in the XWindows system, more specifically in the libx font. So with a specific font file, a user that only had unprivileged user could acquire root privileges. And it affected all XWindows releases in the last 22 years, so it was very common. It was easy to exploit. So it's a simple, I have the code below. It's exactly as it's written there. It's a buffer, and then there was a scanf that reads that buffer with no limits. After this bug was detected, we can see here when it was announced. In 2-3 days, the downloads was exploding. And also after this announcement, the downloads was higher than in the previous months. The Cppcheck development has taken many turns and twists. I have made many design decisions, and some of them was good and some of them was bad. So, for instance, the preprocessor is one case, and sometimes we have had contributors that are not very happy when they invest their time on their free time and spare time, and I make bad design decisions and they waste a lot of time, and then I just remove all their work. So yeah, I'm sad about that. A learning I made was canonizations. We started Cppcheck with this feature. In Cppcheck we call it simplifications. So we wanted to canonicalize the code, so it used fewer constructs. That made the checkers didn't have to handle so many constructs. The learning I made was that it was a good idea when we only had a token list. But as soon as we started to add parsing, it was a very bad idea to have this. It made it harder to detect problems. So we had to rewrite all our checkers and throw this away. Learning I also made was that the warnings must be very clear. This is one of the most important features of a static analysis tool. If a tool doesn't write clear warnings, it will not get very good. It will have a lot of noise then. People will I want to avoid misunderstandings. People can easily misunderstand the motivation why we write warnings if it doesn't clearly show in the warning message. And also there is a risk that people don't understand the value flow properly. So we have in Cppcheck various heuristics why we warn about something. So in the code example we have here, we see Cppcheck will see that the variable I is compared to value 20. And then it will determine, okay, I can have the value 20. And it will both look below that condition, what happens with I, and it will also look above. So it performs both a forward analysis and a reverse analysis of the variable I. And it finds here an array index that I is not good there. So Cppcheck will write a warning there. And it's very important that we point out why we write that warning. People will usually think that we use only forward analysis and data flow. Our philosophy from the start has been to rely on configuration for the checkers instead of hard coding. And this makes it quite difficult to write clear warnings sometimes. Sometimes we want that the same configuration for one function will result in one warning, and the same configuration for another function will result in a slightly different warning. So, for instance, if there is buffer overflows in memset or strun copy, because the buffer is smaller than the size parameter, then it's a quite different matter for strun copy and memset. Learning I also made was that from the start, I wanted to have no false positives in any conditions. I wanted first that Cppcheck is very simple to use. You just point it at some code and it will check it, and there will be no false positives. So with the configuration, you could improve the Cppcheck analysis and avoid false negatives, but there was no indication that the configuration was not very good. Nowadays, I think that it's okay to write false positives if the configuration is not very good. But in those cases, it must be possible to fix the false positive by providing a better configuration that avoids false. Yeah?
Can you explain how
Microphone, please use the microphone.
Can you explain how configuration looks like?
Yeah, it was, preprocessor configuration mostly, include paths, defines, that kind of thing. But we also have those configuration files that can be provided. A learning I also made was that technically correct errors, we detect the problem we want to detect and we write a warning. So from our side, we think that everything is exactly as we designed it to be. That can be considered to be a false positive. We have had many cases when people complained about undefined behavior. Yes, it is undefined behavior, but it works on my code in this compiler. So after those discussions, we have made some undefined behavior portability problems instead. So it's reported as portability problems, and users can suppress those more easily. Then there is a particular syntax error I remember quite clearly. The user thought he ran on his code, and the Cppcheck complained that there was a syntax error here. And the user, when he compiled the code, didn't get the syntax error. So he said that this is a false positive. And I tried to explain that Cppcheck checks all the configurations. And yes, you have syntax error if in this configuration. This if-def is not well written, in my opinion. It shouldn't be written like this. But the user was very stubborn, and there was a team member in the Cppcheck community that told me that you can't save them all. And that was a revelation to me that even if I write perfect analysis, I can't save them all. So when I started, what checkers did I want to implement? I had a very simple goal, keep it simple. So as far as I remember, the rules I thought I would follow was that it should be a common bug. It must be simple to detect. And the pattern that I looked for must be a definite error. There should be no some cases when that pattern is used by intention. But my learning was that there are not many common bugs like that. So nowadays I look for real mistakes that are made in real code and try to identify if this is something I can detect in Cppcheck with a high probability with true positive. I prefer simple analysis, so if there are many checkers possible, I think that the simple solution is good. Some thoughts about synthetic test cases. Sometimes people test various tools using synthetic test cases, and I think it's a bad idea, mostly. Usually those synthetic test cases have various kinds of data flow issues. So they want to test if tools handle different data flow patterns. Typically there are no heuristics, and if there are heuristics, they might not be the real world heuristics that should be used. So a tool that makes a very good performance in a synthetic test suite might not be as good as Cppcheck in the real world. So a word about how we test Cppcheck. We of course have a CI that runs various unit tests and whatnot, fuzzing, dynamic testing, and yeah. But we also check the Debian source code continuously. And the reason we do this is not to see problems in Debian, but it is to see problems in CppCheck. I'm not sure how many have heard of the Boink project, but basically they have a server client solution where the server has work packages, and then clients connect to that server, asks for work, and it's very distributed, so anybody who wants to join that can install Boink and then run analysis, run work. We have something similar in CppCheck. We have a server that contains URLs to source packages, and anybody who wants to help testing CppCheck can run a Python script that we have called donate CPU. So that script will ask the server for a URL. The server just responds with a URL, and yeah, good luck with that. And the script will download that source package. It will download the latest stable CppCheck and the latest CppCheck development version. And then it will compile CppCheck. It will scan the package with both these CppCheck versions, and then it will generate various reports, and those reports are sent to the server. The reports that the server can provide is a crash report, so that we see for each version, CppCheck version, did it crash or not on that source package, and we get a list of all crashes. There is a diff report so that we can see what warnings are generated in each version, what is the diff. And then we have a head report that shows all the warnings that the latest development version shows. Then we have two time reports that compares the CppCheck versions. So if there are regressions, those are shown in the first report. If a package is very slow, that is shown in the other. What does it find in Debian source code? So we have 1900 buffer overflows. We have 16,000 uninitialized variables. We have 8,000 null pointer dereferences. And the total number of errors that we find is 94,000. So errors, that is various kinds of bugs. It's not all are undefined behavior, but it's something we classify as a real bug. And when I look at it, I think that the noise ratio is quite good. So there are many true positives here, but definitely I would say there are false positives also. But I don't have the time to look at all this, unfortunately. I think that if everybody used CppCheck, these numbers would decrease a lot, and the noise ratio would increase. Then it would be easier for us to detect the false positives. We could fix that. It would be beneficial for everybody. So a few years ago, I started thinking that I wanted to work full-time on CppCheck. So there were two reasons I wanted to do that. The first one was very selfish. I like to work on CppCheck. So it was purely selfish. The other reason was that CppCheck has no resources. Nobody is working on it full-time. There are so much that we can't do on a hobby project level that I felt I want to implement features that are just not good enough, but that are better than that. So a solution was to start a company. I started a company together with two friends. So nowadays I work full-time on CppCheck. We have two versions. Open source is free to use. We have an active community. CppCheck is compiler agnostic. It is fast, accurate, easy to use, widely used. And I actively maintain it as part of my work. Then we have a CppCheck premium version that is paid. So the main enhancement in that is it actually uses the open source CppCheck, and then it's just an add-on. It bundles an add-on. So you get additional coding standards, AutoSAR, MISRA, and CERT, and you get extra checkers, a few. It is TÜV certified for safety, and we provide active support of that. But feel free to use open source. We actively support open source in this company. It's very important for us that it will work. Now it's going over to a bit of what has happened over time. And here we have a graph that shows contributors. That is the red line. It's the sum of the contributors, so it's not per month. The blue line is commits per month. So we can see here that the contributors, it was just me until 2008 there, and nowadays there are about 500 in total. Of those 500, not many work actively on CppCheck. Most of them just provide one patch and then they don't do anything more. So they just fixed some problem they have and then they don't do anything more. That is fine. Yeah. And here are the downloads over time. So what happened here in 2016 is that we moved the release binaries to GitHub instead. So on SourceForge, the downloads was dropping quite fast there. Also to note here is that this doesn't reflect the total number of downloads very well. It's when Windows users want to download CppCheck, they probably go to SourceForge or GitHub, but a Linux user will probably use a package manager. So we only have statistics for Windows, more or less. Here are the main contributors of the open source CppCheck project. I will pause a few seconds here. I have contributed about 1/3 of the commits, so there is a lot of commits made by these excellent guys. Okay, summary. I started CppCheck as a hobby project. I had no real ambitions about it. So I didn't think it would be this good at one point. So I couldn't have dreamed from this, and I am so grateful for this. Okay, thank you. Are there questions?
One of your big goals, you said, was to keep it compiler agnostic. Now, compilers, of course, span different versions of the language as it's progressed and have extensions. I assume you must do some sort of rudimentary parsing, but not complete parsing, to be able to handle all the different variants without changing, you know.
Yeah.
Just talk a little about that.
The CppCheck parser is quite special, I would say. It's mostly based, the syntax tree is 100% based on the operator precedence. So the operator precedence is always the same no matter what compiler you use. But there are many things in compiler extensions that we don't understand completely. If there is a declaration in global scope, for instance, and that uses compiler extensions, we don't understand that, but we can still analyze various other functions that don't use that compiler extension. So we don't just stop and bail out.
Right. Thank you for this interesting journey, especially that you also pointed out things that didn't work. It's always interesting to hear about. I was wondering about the performance of the tool over time? Because like any tool should be like as close to immediate feedback as possible, right?
Yeah.
So did you analyze this? Can you tell us something about this?
Yeah, it has certainly gone up. As in recent years, the main problem in that area has been the value flow analysis. So as we increase the value flow, it will significant problems with the performance. We have started to look at how can we make different check levels in CppCheck so that there is an exhaustive checking that is slow but more complete, and then you have a fast checking that is more simple but more direct.
Okay,
But the parser, I think the parser should be possible to speed up. That is my feeling.
So this is a call for contribution, I guess.
Yeah, yeah.
All right, thank you.
Thank you for the talk and also the tool itself. My question is about the language features as the language evolves, other than templates, which I'm sure most toolchain developers will agree is horrible to try to implement. What features have you found it particularly difficult to try to deal with, especially considering you have your own code base and you're trying to make it as compatible and as possible even with older platforms?
Yeah, I would say Preprocessor is also very difficult, and people like to use Preprocessor and templates to write macro magic and template magic to do wonderful things, but the code will not look very nice for us. So handling that when we don't have full information is a big problem. It's a reason why I have thought about integrating Clang AST somehow into CppCheck. But the day we do that, it is no longer compiler agnostic. So it must be, I think if we do that, we will still keep the CppCheck parser that is compiler agnostic. And you will be able to opt in for Clang AST. But it's not also clear to me how to integrate Clang AST in a good way. For instance, because we don't want to use the latest C++. We want it to be portable to a range of platforms. Okay?
So if I had, thank you for the talk. Thank you for working on static analysis tools. These are always there's a really high return on investment for all the time you put into this, like for the whole community, so that's great. I wanted to ask you, as someone that maintains a lot of these tools, which kinds of upcoming C++ language features are the most concerning for you, as far as like how much time and effort it's going to take to catch up with that particular feature?
Maybe I have to pass a bit on that. I'm not sure. But coroutines is maybe one. On the other hand, if I can say that, I think I look very much forward to some other features like contracts is something I think we can use in CppCheck. I think reflections, as far as I have seen so far, is scary. Yeah.
Have you taken a look at modules yet?
What?
Modules could go either way depending
Yeah.
on how you work, your stuff works, right?
Yeah, no, I haven't looked very closely on that yet. We are trying right now to integrate as much as we can in C++20.
Can you talk a bit further about owning a company? I mean, most of us here, I assume, are developers, and like we don't know about business and stuff like that. And I don't know about you, but like to me, it sounds like scary to go from something you just do on your own and like having a company and doing negotiations and all that.
Yeah, we had the approach that we wanted this to grow gradually. I mean, I didn't stop working full time. I worked 90% on my full-time job to pay the bills. and I started the company. And then after about a year and a half, we had enough customers, so I could start working full-time. So I didn't take a real economic risk there.
Sorry, I have a lot of questions. I'm sure we can catch up more on the hallway. Something that's been interesting in recent years for the C++ ecosystem is called sarif, the Static Analysis Results Interchange format. You're nodding your head, you've heard of it.
Yeah.
Is that on your roadmap to produce those results from CppCheck?
Yeah, there has been work that I was not 100% happy with, but there is interest in that, and yeah, I think in a half year there will be sarif output directly. But I know that there is a script that can convert a CppCheck XML into sarif also right now.
Yeah. Maybe to save you the effort of writing papers or contacting ISO committees, there is a proposal to like make that more of a thing that we expect from different tools in the ecosystem. Do you have any like quick thoughts on like, you said you weren't super happy about that. I was just curious if you cared to expand on that, given we have some time.
No, it was more not about the sarif output, but I wasn't super happy about the implementation in CppCheck.
Okay, I gotcha. So like to implement it for your tool, okay, I get what you're saying. Yeah.
But yeah, I think it's in our work map and we will implement it.
Do you have any thoughts then, like what pros and cons of it? Maybe you haven't had a chance looking deep into it or something.
I really like to have a common format for all tools. Maybe in the future it will be much easier to reuse different tools in the same plugins. So for CI and in IDEs perhaps also, if the tool can output sarif, you can easily run it. That would be great.
All right, so no one else has questions. One of my concerns about the ecosystem is around static analysis and how it's not portable to educate your static analysis tools about what you mean to do with your code. Typically in other ecosystems you would have, including, by the way, using specifically things like clang tidy, there's non-portable ways to say, this is not an issue, trust me, I have a comment or something I can point at. The ticket that, like including in highly regulated environments, this one doesn't count. We've talked about it, it's been approved and tested to death, it's fine. We don't have a portable way to do that though. So like, do you have any thoughts about like where we could go as a community to make it easier to say, as CppCheck, warnings, clang tidy all complain about the same line of code, but then tell all of them to go away at the same time?
We have not had any active discussions about that, but I like the idea.
Cool.
I just figured I'd give you an excuse to get off the mark.
I need to catch a breather.
I want to say thank you, of course, for your work. I've recommended and used CppCheck for a long time. But a minor annoyance I've had lately is when I'm using like C++ 23 syntax or something like that, like pushing the envelope, then I get syntax error from CppCheck when all of my compilers compile it just fine. So I've had to go through and like manually say, no, please don't give me syntax error reports. And I don't know, I'm just like trying to figure out the balance there for like, yes, I do want all the warnings, but it's valid C++, it's just not syntax CppCheck supports yet.
Yes. I have the feeling going forward that as we are a commercial company now and have some resources to work on this, I have actually, there is a contributor here in the USA that I have said that he can work on improving this language support, and we will pay for that. Okay. So I hope going forward that it will be better.
All right, thanks.
Thank you for the talk. I have a question regarding, do you also prefer to give some design pattern checks through CppCheck, like suggestions or?
Yeah, I think design pattern checks is not possible in our core philosophy. There are, in my opinion, some people like this design philosophy, and so. But I think that in either add-ons that I would be happy if somebody writes an add-on. It's a Python script that contains various design patterns. That would be nice. And I know also that there are customers that request this, so we have active look at this.
Hi. First, thank you for your work. It's caught a lot of my bugs. One thing that I've heard throughout the community is it becomes difficult to kind of gather all of the tools that you need to really catch all of the issues. Has there been any interest or reaching out to maybe integrate CppCheck into the various compilers directly?
Yeah, well, a little. CMake, for instance, has direct handling of CppCheck, and but it's not perfect in CMake handling. But I want to talk with them and have agreed after this CppCon to talk about them with that. So if you use CppCheck in the future and integrate in CMake, it will work better. The problem that doesn't work very good right now in CMake is whole program analysis. But then there are tools, there are providers that also integrate different static analysis tools in a common platform. So that is also, I have thought from the start that I don't want CppCheck to be like tool for everything. And therefore I was hoping 17 years ago that there would be lots of such tools that would aggregate lots of tools into one common interface. Yeah, I would be happy to discuss CppCheck further later, so I will be here the whole week. Feel free to come. Thank you.